make sure everything's clear. This week, you're gonna bring your lab manual with you, right? That's the one with all the procedures in it. You don't bring your notebook at all. You don't need your notebook this week. And the pre-lab for this week is when you look at experiment 15 in the laboratory manual, questions 1 through 4 ask you to draw Lewis structures as well as answer some other questions. The pre-lab is to draw those Lewis structures. Just, you don't have to do the hybridization or the bond angle or the polarity. Just the Lewis structure for those questions 1 through 4. What we're going to do in lab is you're going to finish the rest of those questions, do the bond angle, hybridization, polarity. You're also going to answer questions 5 and 6, which have to do with Lewis structures. Okay, is that clear? Everybody clear on that? You know what you're going to do? So, no notebook this week? What's that? Who said that? Yeah. No, it doesn't matter. You can use a pencil if you'd like. And if you're saving your lab manual, if you don't want to write in it, that's okay. Just make copies of those pages and bring them in. Okay. Now, is that clear? So we are in chapter 10 here. Chemical reactivity. One way of classifying chemical reactions is based on what the atoms are doing. So that would be these would be the 4 basic types of chemical reactions, classifications based on what the atoms are doing. We saw some combination reactions last time, the end decompositions actually. For example, I talked about, do you guys remember metal oxides reacting with water to make metal hydroxides? And there's that figure in your textbook that tells you which metal oxides will do that, which I asked you to memorize. So, for example, sodium is one of them. Decomposition reaction, it's really kind of the opposite of a combination reaction. In a combination reaction, you have 2 things usually combining to make one. In a decomposition, you usually have 1 thing breaking apart into 2 or more substances. For instance, mercury 2 oxide. This triangle just means that you have to heat it up to make it happen. Heat makes liquid mercury and oxygen gas. A few more decomposition, classes of decomposition reactions that you should memorize or know are these. metal carbonates. When heated up, they'll form a metal oxide and carbon dioxide. Another one is metal sulfites. When heated up, some of them decompose to a metal oxide and sulfur dioxide. Metal sulfates. So a sulfate will decompose into a metal oxide and sulfur trioxide instead of sulfur dioxide. And a couple others that you should know. This one is used in the lab sometimes to generate oxygen. This is called sodium azide, and when it breaks apart, it makes nitrogen gas. It's a solid. It makes nitrogen gas and sodium. Right. This is one, the book talks about it, that they use, it's commonly used in airbags in cars to inflate the airbag. You have a solid right here, which doesn't take up much volume. Solids take up really little volume compared to gases. And this is a gas, right? So the gas, when it's produced really quickly, inflates that airbag. So pretty much just that. This is just stuff you have to know, so just memorize it all. Next type in that list, there's combination, decomposition. The next are single replacement reactions. plus a compound. What happens is, this is really general form of it. I'll show you specifics in a second. But whatever type of element this is, for us it's either going to be a metal or a halogen. Those are the only ones we look at. We'll displace the similar type of element in the compound. So if this is a metal, for a single replacement reaction, there'd be a metal in the compound somewhere. And what happens is, if the reaction occurs, this metal will replace this metal here. And element 2 would be the metal that was in here is now by itself. And the compound 2 is this compound with this metal in place of the first metal, for example. For example, magnesium would be the element here, and the compound is chromium 2 nitrate. Well, what's happening in this single replacement reaction is the magnesium metal is displacing the chromium, it's replacing it, right? So now you get chromium kicked off by itself, so it's chromium metal, and you get magnesium nitrate, it's aqueous here. An example of one of these where it's the halogen would be this. Here the element is fluorine, the halogen. The compound is potassium iodide. And so what's happening is the halogen, fluorine, is replacing the similar type of element, the halogen, which is iodine. So fluorine is replacing the iodine. We get iodine now by itself, and potassium fluoride over here. You guys see what happened? It ends up that if I switch these around, try to do the reverse reaction, nothing happens. Same thing with the second one. No reaction. Let's look what this means. Let's look at what this means. It helps to write, I think, with these the net ionic equation. You guys remember that from Chem 42?
Yeah.
You do? The rest of you guys? No? Yeah. I hope my 142 students do. We'll see. I'll probably review complete ionic and net ionic equations a little bit later on, but it ends up, okay, for now I'll just write the net ionic equation, and I'll review it in a little while and show you how to figure it out if you don't remember. For this reaction right here, the net ionic equation would be okay. You guys buy that one? Those of you that remember net ionic equations? I'll go over that a little later. But anyway, accepting for the moment that this is the net ionic equation, this shows the chemistry that's going on there. And what's happening here, magnesium has no charge, it's metallic magnesium. Chromium has a positive 2 charge. Over here, chromium has no charge, it's metallic chromium, whereas magnesium has a positive 2 charge. In terms of electrons, what had to happen to the magnesium? Right, it lost 2 electrons, right? What about chromium? What's happening to it? Gains 2. So electrons are moving back and forth, right? And so what that means is, because it goes this way, chromium must be more stable with those electrons than magnesium is. You guys buy that? Because if it were the other way around, then magnesium wouldn't release the electrons. If this is more stable with the electrons than this is, this reaction won't occur. Which is why, when you try to write it the other way, the net ionic equation, if it were to occur, it doesn't happen because chromium is more stable with those electrons than magnesium would be. So it doesn't release the electrons. You guys buy that? Does it make sense?
I don't know, like, all you're saying is balance out the charge, right?
I'm not even balancing. All I'm saying is that let's look what's happening with the electrons. Okay? Where are they going? Where are they coming from? In this one, okay, what I'm telling you, first, when I said first, was that this reaction happens, and I'll show you how you can figure that out in just a minute, but just for now, take it that this one does, but this one doesn't.
Okay.
Okay? And because this one happens, you can see that magnesium is releasing electrons onto the chromium grounds.
Okay.
And that must, and because if we try to do it the other way, if we try to take electrons from neutral chromium and add them to magnesium, it won't happen. Which means chromium must be holding them more strongly than magnesium is. Then magnesium grabs them. And what that really means is that chromium is more stable with those 2 electrons than magnesium is. Think about that? Make sense?
I get it now.
Okay.
Thank you.
Yep. The way that you can tell whether or not a reaction as written will occur, a single replacement reaction will occur as written, is table 10.8, called the activity series. It's on page 325, and I will not ask you to memorize it. I'll give you this one if you need it on the exam. So let's look at that. If you have your book, please turn to that page or look at somebody. Because even if I give it to you, if you're not sure how to use it, it's not helpful to get how to use it. So let's look at those 2 metals that I was just talking about, magnesium and chromium. You guys find them in there? Right. Magnesium and chromium. The important thing here in this table is that magnesium is higher up in the table than chromium is. What that means is it's more active. Magnesium is more active than chromium, which means it will release its electrons more readily than chromium will. Okay? Which means that this reaction will happen because magnesium releases its electrons, chromium grabs them. But the opposite reaction won't happen because chromium's less active than magnesium. Another way of saying that is that a metal that's higher up in that chart will displace a metal that's lower in the chart, but not the other way around. So stuff falls downhill easily, but it doesn't go uphill as easily. Okay. See how that works? So now you can, for instance, one more addition. There's a really important element that they neglected to put in here, and that is hydrogen. Hydrogen should go right between lead and copper. They kind of imply it with what they tell you, but it works to put hydrogen right between lead and copper. You guys see what that is? So please do that. I will do that for you when I give you the table on the test. But when you're doing homework and stuff like that, you probably are going to want to know that hydrogen is right between lead and copper. So, So the question is, what's the balanced equation for the reaction, if any, between metallic tin? When I say metallic tin or whatever, it just means the element by itself, solid, and aqueous zinc sulfate. So the reactants then would be what?
Tin.
Tin. What's the symbol for tin? Do you guys know?
SN.
SN. What's the formula for zinc sulfate? Aqueous zinc sulfate.
ZnSO4.
So, I mean, you know that I'm talking about a single replacement reaction because that's what we're doing right now. But on the test, you would. The way that you would know that it's a single replacement reaction is because it's an element plus a compound. So the first question is, does the reaction occur? And you guys tell me. So you're going to look at the activity series.
Yeah.
You think so, Devin?
No.
But Adam says no.
Zn's below Zn, right? Sn is below Zn.
SN's below Zn, which means it's less active, so it won't occur. The reaction will not occur, right? Do you guys see how that table works? Yes. what you do, okay, so whenever you come across a single replacement reaction, like this is, if they're metals, I'm going to explain about halogens in just a second. They're easy. But what you do is you find the two metals in the activity series. One's going to be in a metal by itself in this equation, one's going to be in a compound. But you just look up the metals, right? And so, in order for that reaction to occur, the metal that's in its elemental form by itself has to be higher in that table than the one that's in the compound. If it's not, then it doesn't happen. The reaction doesn't happen. Because, and in this case, tin is lower than zinc in the table. So we first of all, we predict that this single replacement reaction will not occur as written, and it won't. And you know, we can think about that as the tin holds on to its electrons. It's more stable with those two electrons than the zinc would be. So it doesn't happen. You guys okay with that now? See how that works? So I'll give you the table, you just have to know how to use it. The opposite reaction though, you think that's going to happen? Sure. Can you tell me what the products are there?
SN plus ZnSO4.
Exactly. The other type of single replacement reactions you'll see, as I pointed out a minute ago, are the ones where the element is a halogen. It's just the same order as they are in the periodic table. In other words, fluorine's more active than chlorine, which is more active than bromine, which is more active than iodine. So fluorine will replace chlorine or chloride ion in the compound, but not the other way around. Look at this potential single replacement reaction. And again, you know that this is a single replacement reaction, or at least potentially, because it's an element and a compound. When that happens, this element you'll see if it will replace that similar element in the compound. Here, the halogen and the halogen. So from this series, you see that fluorine is more active than iodine. So it will displace it. And what do you think the products will be?
2Na. Oh, right.
I2. And what is that, solid, liquid, or gas?
Solid.
Gas.
See on that table right there? It's black. That means that it's the elemental form is solid at STP, at these conditions. Right? You guys, I told you about that periodic table, right? What does the blue mean, remember? Liquid, right? And red? Gas, right? So, but you knew that from the lab anyway. We've used iodine in the lab before. Remember that dark stuff that stained your fingers? Yeah. What else here? What else? Sodium fluoride, NaF, right? not NaF2.
No, because the iodine second.
It's only 2. Hofbrinkel only applies when it's in its elemental form. I told you about Hofbrinkel. No?
No? Is he?
German guy.
Did I mention? I know in 142 I did, right?
You did in here too.
Buddy did it here also.
Yeah.
It's just a mnemonic for remembering the 7 diatomic elements: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. I did.
Say that
Yeah.
a little slower.
I don't think I can. It's just, I mean, it's a nonsense word, but for some reason it's easy to remember. Hofbrinkel, right? And it's just, it's the sounds of the 7 diatomic elements: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. In their elemental form, under standard conditions, these elements are diatomic. So it's I2, Cl2, Br2, N2, O2, F2, so on. It's just a way of remembering. But anyway, fluorine and iodine are both. It's okay?
I got it.
Good. And obviously, I hope the reverse reaction would not go. You guys understand that? Those are single replacement reactions. Double replacement reaction. In general, double replacement reactions look like this. The underlined ones would be the cations, the others would be the anions. So what happens is, in general, in a double replacement reaction, the reactant, on the reactant side, the cations switch anions, right? So this is with B, it pairs up with D. This is with D, it pairs up with B on the product side. See that? For example. So these are 2 ionic compounds. Potassium is a cation here. Lead-2 is a cation here. You can predict the potential products by switching cations with the anions, right? So you're going to take lead-2 and pair it up with the chlorine ion. What's the formula for that?
What?
What's the formula for the compound, at least potentially, that would form between lead-2 and chlorine? CDAC.
Yeah.
Yes. And what's the other compound on the product side then? I'm sorry?
Potassium.
Yeah, potassium nitrate.
Nitrate.
We're going to have 2 of those. And I think that's balanced together. So this is an example of a double replacement reaction. And one of the things you'll be doing is what we just did, predicting the products, right? And then balancing it, like I did. Now, this one here, let's try that. Won't happen. No reaction. And the reason is that if we do the same thing we did over here, and we switch cations, we get these products. See, the difference between this reaction and this reaction is that here, one of the products is not aqueous. It means it doesn't dissolve in water. It's a solid in this case. Whereas in this reaction, everything's aqueous. Right? And whenever that happens, we say no reaction occurs. And that's because of this. One way to physically try to do this reaction would be to start out with two beakers. In one of those, you have some silver nitrate that you dissolve in water. And in the other, you have some lead-2 acetate that you dissolve in water. And then you take those two beakers of solution and you mix them together. So here's what it would look like. Yeah. First beaker. They're all aqueous solutions here. And the silver nitrate, aqueous means that it's dissolved in water, which means that it's separated into its ions, silver and nitrate. The second beaker, there's lead, 2. And acetate. When we pour these together, say in a bigger beaker. We have the same thing. Nothing's changed, no reaction. We have aqueous ions over here, same aqueous ions over there, no reaction. On the other hand, if I do the first reaction, which was potassium chloride and lead nitrate. When I mix these two beakers together, initially, the very instant we mix them, we'll have all these ions in there. But they're moving around. You know, in solution, these ions are constantly in motion, and real quickly, there's lots of these, like, you know, like 10 to the 23rd of them, right? Something on that order. Whenever a lead ion bumps into a chloride ion, it ends up that it grabs it. It doesn't let it go. And it grabs the second one too. And it looks instantaneous. Right away, we start getting this solid, the lead 2 chloride forming. We still have the other ions in solution. We have the potassium and the nitrate. They bump into each other, they just fly right apart again, right? They're aqueous, they're soluble. If a lead happens to bump into a nitrate, it just comes right apart, like that side. But here, something happened, something changed, a chemical reaction occurred. So then the next question is, how do you know if something is going to stick together or not, or something will come apart? That's called the solubility, and there's a list of rules. On page 329 at the top, you definitely need to know these. These you should memorize. Put on your card. If you had 142, there's some differences in here. So don't rely on remembering the stuff from wherever you had your other chemistry. These are probably slightly different. Did I say 329? So let's see. A couple of different ways that you'll use the solubility tables. One, a multiple choice test. You might say, which of the following compounds is soluble, A, B, C, D, or none of the above? Or which of the following is insoluble in water, A, B, C, D, or none of the above? So all you do is you apply the rules to each of the compounds, find the one that's soluble or insoluble, if any. The other way is a problem like this. right, so you're going to use your solubility rules here too. And the reason is this little phrase right here, if any. Because this is going to be, if it happens, it'll be a double replacement reaction. It's an ionic compound, mercury 1 perchlorate, and another ionic compound, potassium carbonate. So if the products are both soluble, based on those solubility rules, then the answer is going to be no reaction occurs. But if you get at least one product that's not aqueous, doesn't matter actually if it's solid, liquid, or gas, as long as it's not aqueous, then the reaction occurs and you write a balanced chemical equation. So let's do it. What do you think the first thing is that we should do? Make sure what? Well, if I say aqueous, then you can probably trust me, but if you don't, figure it out. Okay, but actually that's a good plan. It lets me start to use rules. If the question was, is mercury 1 perchlorate soluble? Okay, you should look at the rules. If you guys have them, it'd probably be a good thing to look at them now. And that second rule, number 2, says that most nitrates, acetates, and perchlorates are soluble. Right? The way this table works, again, it's different than the one in Chem 142 that we used. This is hierarchical. If two rules conflict, the one that's higher up that has a lower number predominates. Right? See how that works? So if you look at rule number 1, it says that the alkali metal salts and ammonium salts are soluble. That takes precedence over anything else. So that means that basically, if it's in the first column, lithium, sodium, potassium, rubidium, or cesium as the metal, with any anion, that's soluble. And the same thing goes for ammonium and H4+. The second rule, nitrates, acetates, and perchlorates, this is talking about anions, they're soluble. So what that means is that, because that's the second rule, no matter what the cation is, those three anions will make a soluble compound, which is this one right here, mercury 1 perchlorate. You guys know the formula for mercury 1 perchlorate? ClO4 is perchlorate, yes. So let's write that down, ClO4 minus. What's the formula for mercury 1?
HG plus.
Yes. It ends up that mercury is weird, okay? It's the only element that does this. It's mercury. The mercury 1 cation is diatomic. In aqueous solutions. I mean, it's more complicated than this, but we're only dealing with aqueous solutions. So whenever you see mercury 1, it's always Hg2, 2+. You guys are never going to have Hg plus for mercury 1. So let me write this over here for you to memorize. Just memorize that. Once you realize that, then you can see, hopefully, that the formula for mercury 1 perchlorate will be aqueous. You guys buy that? No, they don't do it here. Yes, I do. Thank you, Deb. I appreciate the confidence. And again, it's aqueous, which means it's soluble because of the second one. Aqueous potassium carbonate. Formula?
Okay.
Potassium is +1. Carbonate is CO3. And you guys remember the charge?
2 minutes.
So K2CO3. And it is also soluble. It's aqueous. You guys see which rule in that list tells you that it's soluble?
Carbonates. Rule 5, right? Most carbonates?
Well, rule 5 says that most of those things are insoluble,
Oh.
which means not aqueous, but solid. The first rule, though, see, the first rule says that alkali metals and ammonium salts are soluble. Potassium is an alkali metal. That's the first column, right? And so those two rules conflict, right? Rule number 5 says that carbonates are insoluble. Rule number 1 says that when the alkali metals are the cation, they're soluble. Rule 1 trumps Rule 5, so it's soluble. You guys see how that works? So yes, it's soluble. Now, the next thing we want to do is figure out what the potential products are. And to do that, cations and anions switch places, right? This cation goes with that anion and vice versa. So can you tell me what at least the potential products are? We'll do solubility in a second.
Potassium.
All right, so let's go with this cation first. Right now it's with perchlorate. So we're going to switch it and combine it with what? What are we going to combine it with?
Carbonate.
Carbonate. So what's that formula? When mercury 1 combines with carbonate. It's Hg2, because remember, it's mercury 1 is always Hg2, 2 plus, right? And then what?
CO3.
And again, that's because this has a -2, this has a +2, they cancel each other out. So it's 1 to 1. What's the other product? Potassium. Potassium perchlorate. What's the formula? Is it K2 or K?
Okay.
2K.
Okay, we'll balance in a second, but the formula is just NCl, right? And again, that's because potassium has a +1, perchlorate has a -1. So again, a lot of times people see the 2 over here and they want to keep it as K2. Don't do that. It's just the ion that you're looking at. Potassium +1. So, okay, you guys realize that it's not balanced. How should we balance it? Put a 2 here. Everything's good, right? Now the solubilities. The mercury 1 carbonate, soluble or insoluble, and why? What rule tells you that? Sorry? Insoluble, okay, and which rule? Ready? Oh, okay. Yeah, sure. Mercury 1 and also 5, right? 3 and 5 both, you're right. So it's a solid. What about potassium perchlorate? Aqueous, it's soluble. Rules 1 and 2 both, right? So there it is. That's another way you would use the solubility rules. Third way. This is a fun one. It's a problem like this. Any questions before I erase this? Anything you guys want to ask about it? Okay, Sam?
No. We still have
this is actually a simplified form of what you guys do for about half the semester in lab in Chem 102, qualitative analysis. So look at that for a second. So we have to come up with a procedure. In other words, add this, add that, do that, right? Sky's the limit. What do you think? So here's a picture. A big beaker. We don't know what's in there. It could be one or all four of those, right? Obviously, because that's what I'm talking about now, we're going to use the solubility rules, right? So what do you think? I'll start you out. What's that?
Taste it.
Taste it. Let's see. That's probably not too good for you. That's probably not too good. So you taste it, and if you fall over, then you'll know that we're one of those.
Would it be NH4 plus? Would that be aqueous?
That what?
Aqueous NH4 plus?
If it's in there. This is all an aqueous solution. So there's water. It's a beaker of water.
Just
right?
throw it all in there.
And no, see, the thing is that, okay, let's say they're all in here. Okay, there's one or more of those in there. So we already have this solution. We don't know what's in there, but it's one or more of those. Okay, they're already in there. We want to see if they're in there or not. Anthony?
Can you just add something into it and see if the solids form?
Exactly. That's the point, right? And so we're going to use the solubility rules to figure out what we should add, right? And the order is going to be important. So take a minute, look at the solubility rules, see if you can figure out what you want to add first. First thing you want to add. They're all cations, so it's going to be some anion, right? You guys understand what I'm asking you to do? So pick something from that list to add first. Yes,
Sulfate,
I like it. That's what I picked too. Why did you pick sulfate?
because it's at the very bottom, and
And-
you can rule out stuff if you keep going up.
So what happens? So excellent, right? So what happens if we add, let's say, sodium sulfate? So here's our procedure. I mean, just sodium sulfate, it doesn't matter as long as it's soluble, right? I know sodium's going to be soluble. What happens when we add sulfate into here? If it bumps into ammonium, is anything going to happen?
No.
No, because ammonium sulfate would be soluble, you see? Okay. What about lead 2?
Just barium.
Is that
Just barium.
just barium, right? Actually, let me change that lead 2. Let's call this. Iron. Well, barium is the one that's going to precipitate out for sure, right? Because sulfate, right? And so, if barium is present, then we'll pull that out. If there's a precipitate, we want to filter it out so that all that barium is gone. It's not going to interfere with anything else. What next? So that's gone. Sulfate and barium are gone. What do we want to add next? do you think? Any ideas? Anything? Pick something out of here.
Oxide?
Peroxide?
Add uranium.
What's that?
Add uranium.
How about something cheaper? How about salt? So, that's my suggestion, okay?
That's your suggestion.
We add sodium chloride, basically we're adding chloride, right? What's gonna happen?
It's gonna bump into lead.
Into what?
Into lead.
The lead, right? So if it bumps into ammonium, nothing happens because ammonium chloride is soluble. If it bumps into copper too, same thing, right? Because the rule, is it 3? Says that chloride, no, which rule is it? It says that
3.
chlorides, bromides, and iodides? 4. Chlorides, bromides, and iodides are soluble. So bumps into that, nothing will happen. But rule 3 says that lead 2, or lead compounds with chlorides will be insoluble. So we get that. And then you see why I'm saying filter the precipitate? Hey, Wendy. This is Wendy, she runs the division. Oh, today?
Yeah.
Oh.
Do you want me to not?
No, it's fine, it's fine. Let me just finish this.
Yeah.
Give me 2 minutes, 3 minutes.
Yeah, we need about 10 minutes.
Okay. So the lead 2 will pull out any chloride, and if there's any, you want to filter that, that way all of the lead is gone, it's not going to interfere with anything else, right? So now that's gone. Okay, it's getting down there. What else should we add? What's that?
NO3, like a nitrate to knock out the ammonium.
How would that do it?
Just wild gas.
You're pretty close, okay? But let me give you a hint. Concentrate on the copper first.
Okay.
Then we'll deal with the ammonium. Any ideas? I thought I heard somebody say something. Pick something from that table. An anion. Carbonate. Who said carbonate? Somebody did. There, way back there. Yes, I like carbonate because we know that carbonate will react with the copper 2 to make copper 2 carbonate, right? Because the rule tells you that most carbonates are insoluble, right? So add some sodium carbonate. And filter. So that pulls all the copper out. It's gone. We have ammonium left. I have to let Wendy give out the surveys. So we'll do ammonium next time. Okay, on Monday. I'll say that again.